Thermodynamics, Chapter 3, Lecture 3. In the region to the right of the saturated vapor line, and at temperatures above the critical point temperature, a substance exists as a superheated vapor. Compared to the saturated vapor, superheated vapor is characterized by the following properties: lower pressures, higher temperatures, higher specific volumes, higher internal energies, and higher enthalpies. So this graph shows a picture of the temperature versus specific enthalpy, H. So here you can see the Hg value. So for superheated steam, the enthalpy, H, is always greater than Hg. So if we determine our problem is dealing with a superheated vapor, then we want to go to tables A6 or A6E, depending on if we're using metric or English system. So here's a partial list of tables A6 and A6E. And so again, you have to be kind of familiar with what you're looking at here. So you have temperature, you have pressures. These pressures usually in terms of million pascals. Specific volume, internal energy, enthalpy. Let's take a look at an example. Example 3.6. Determine the internal energy of water at 20 psi and 400 degrees Fahrenheit. So this problem, you can kind of guess that, hey, we're dealing with a superheated vapor the way the problem is stated. It's a big title, internal energy of superheated vapor. But in general, we're not going to know what the state is in. We're going to have to determine that for ourselves. So it's good practice to be able to do that. And the homework problems are not going to come out and tell you either. So the first step is to determine the initial state. So here we're in the English system, we're dealing with water, so we're going to go to table A5. And at table A5, we're going to look up the pressure. So the pressure at 20 psi, here we go, come right across. What's the saturation temperature? 227.92. Well, we're at 400 degrees Fahrenheit, so we're well above the saturation temperature. So therefore, that's how we determine that we're in the superheated region. So now let's go ahead and work the problem. We can't come over and use these U values here because, again, now we have to shift tables. We have to go to the superheated tables. So now that we know we're dealing with a superheated vapor, we can go to the superheated vapor charts. Since we're in the English system, let's go to table A6E. So if you look at table A6E, it's laid out a little bit different than the saturated water table. Here, the pressures are given in segments, and so we have to find our pressure first. So since we're at 20 psi, we're going to look in this middle region here. And we're at 400 degrees Fahrenheit. So we come down to 400 degrees on the left first column, and we come all the way across to the 20 psi tab. We're looking for the internal energy, which is U. So here's our value, 1,145.1 BTUs per pound mass. And so that's what our value is right from the table. Let's take a look at another problem. Determine the temperature of water at a state of pressure equals 0.5 million pascals and enthalpy equals 2890 kilojoules per kilogram. So again, the first step is to determine what initial state we're looking at. So here we have the metric system. So let's look at table, and we have a pressure. So let's look at table A5. So if we look at table A5, first of all, we notice that the pressures are in kilopascals. So 0.5 million pascals equals 500 kilopascals. So if you come down to the table of 500, let's slide over and look at what the Hg value is for 500. It's 2748.1. So since our H value, our enthalpy, is 2890, which is greater than our Hg, we know we're in the superheated region. So now let's go to the superheated tables. So now let's proceed to the superheated tables. So here we have, since we have a metric system, let's go to table A6. If you go to table A6, we're not given the temperature or pressure, we're given the enthalpy. So we've got to kind of go into the table a little bit differently. Used to, we'd come over here to the first column and kind of go down and then across, but we don't know what the temperature is. That's what we're trying to find. So we have to kind of go in with what we have. We know that we have an enthalpy of 2,890. So if you look at the table, so the first column, the first row here is at saturation, but the second row is at 200 degrees C. It's 2850.6, a little bit more than that. But the next entry at 250 degrees C is at 2957.6. So our value is somewhere in between here. 2890 is between these two values. So if we come over, we determine that our temperature is somewhere between 200 and 250 degrees C. So how are we going to find the exact value? Well, what we're going to do is we're going to have to interpolate. So here's our information. So we have at 200 degrees C, it's at 2,855.8. At 250 degrees C, it's 2,961. So use your calculator. This is where you're going to have to pull out your calculators. You're going to look up your manual, and you're going to have to figure out exactly how to do this interpolation unless you want to do it by hand. If you do interpolation on the Texas Instruments or any Casio, whatever you have, you can determine that by linear interpolation, the temperature is 216.3 degrees C. So at 216.3 degrees C, the enthalpy is 2,890 kilojoules per kilogram. So this is something else you're going to have to practice. You're going to have to practice this interpolation because you don't want to, you can't figure it out on a test. You have to practice this skill to get good at it. Compressed liquid. So one last region to look at. So compressed liquid, we're over here in this region here. So the properties of the compressed liquid, that they're at a higher pressure. This is compared to a saturated liquid. They're at a higher pressure, lower temperature, lower specific volume, lower internal energy, lower enthalpy. So you can use this table to sort of determine what region you're in. If you're given H, compare it to HF to see where you are, or compare the specific volume to the VF. Now there's two ways to go here to determine the relations. The one that I like to use actually is this first one here. Any property of a compressed liquid is approximately the specific fluid, the VF values, or the F values. So at that specific temperature. So here, Y could be either the specific volume, the internal energy, or the enthalpy. And this is an approximation. It's approximately true, but it's there's very little difference, and it's a little bit more accurate way to determine the enthalpy is this other formula. But honestly, it's not worth the effort. It's usually less than 1% difference between the two. So the bottom line is that given pressure and temperature, use these relations here. The specific volume is approximately VF at that temperature you're at. The internal energy is approximately UF at that temperature, and the enthalpy is approximately HF at that temperature. This is an approximation, but it's very good to approximate it as the saturated liquid at that temperature. Let's take a look at example 3.8. Determine the internal energy of compressed liquid water at 80 degrees C and 5 million pascals using part A, data from the compressed liquid table. Part B, the saturated liquid data. What's the error involved in the second case? So first of all, even though, again, this problem says it's a compressed liquid, we need to actually go in and check and see. So what we're going to do is we're going to look in table A4 because we're in the SI system, and we're given the temperature. So we look in table A4 for the saturation pressure, and it's 47.416 kilopascals. So if we're at 5 million pascals, we're way beyond the saturation pressure. So therefore, this is going to be a compressed liquid. In fact, if we look at it on the chart, if you graph, again, you have temperature on the vertical axis, and here we'll graph the internal energy on the horizontal axis. The green curve is always the same, and so the temperature is going to go up, across, and up. And so here is 80 degrees C right here. So we're definitely a compressed liquid. So here we're going to use the compressed liquid table. So if you go to table A7, and I've clipped a part of the compressed liquid table. You can see here for a pressure of 5 million pascals, which is where we are, we can look up what the temperature is. So at 80 degrees C, we can run across and find what the internal energy value is, 333.82. So that's using the compressed liquid table. So let's go ahead and look at the other way to do it. So here we can go back to the saturation table and let's find use of F at 80 degrees C. So if we look in the table, here's 80 degrees C. Let's run across and find use of F, which is the value right here, 334.97. So that's the approximation. So how much air is involved? Well, we can subtract the difference, divide by the actual value. So it's about 0.34%, which is less than 1%. So again, typically I tend to use the approximations from the saturation table for a compressed liquid.